Welcome, everyone, to my talk. This is sort of a last-minute addition to the show this year, tracking aircraft with Redis and software-defined radio. Let me get my pointer here, get my poop in a group, as my mom used to say. Oh, no, my pointer's not working. There we go. You know, it's always the little things, right? Like, I can literally point with it, like over here, right? But when I try and advance the slide, it won't advance the slide. So we'll start again. There we go. So welcome, everyone. My name is Guy Royse. I'm a developer advocate at Redis. I always like to say there are three things that matter on this slide, but there's actually more than that. There's a thing that matters to all y'all. There's a thing that matters to me. There's a thing that matters to my boss. The thing that matters to my boss is right here, that Redis logo. That's where I work. He would like everyone to know, and honestly, I would like everyone to know that Redis is more than just a cache. It can do lots of things. One of the things we're going to explore a little bit today is that Redis has event streaming data structures. So you can do event streaming like Kafka, but like lighter and more compact, but very fast. So we'll look at those a little bit today. But mostly this talk is about radio, software-defined radio. And so the thing that's radio related that matters to me on this slide is that call sign right there. That's my call sign. I'm a licensed amateur radio operator in the United States. I've got a little radio here with me that I'm not allowed to use in Norway. So I won't. Because I don't want to pay a big fine that's probably a ratio of how much money I make. So these are things that matter to me. I've also got my Twitter profile on there if you want to give me a follow on Twitter, if you're still into that. I know a lot of people aren't. But the part that matters, the part that really matters on this slide is the github.com/GuyRoyse URL. So all of my code for what I'm going to show you today and my slides and stuff are all out there on GitHub. So if you want to go play around with this and go buy some gear and say software, you know, I saw this talk and I thought software-defined radio was awesome. I want to go buy all this stuff and do it, and I want to run the thing Guy ran. You can go out to GitHub and find your information there. So I want to set some expectations for this talk before we get started. So first and foremost, I am not an expert. I am a fan. I've been getting into radio for the last about year. Got into software-defined radio before that. I'm still learning. It's a big space. There's a lot to learn. So I could be off on some of my details. But the stuff that I know, and the stuff that I don't know, I can speculate on. And then there's that area in between where I think I know something, but I'm wrong. There might be a couple of those in here. Well, hopefully not. There's going to be a lot of demos. I basically have a bunch of toys, and we're going to play with them for an hour. Does that sound fun? All right. I heard a woo. That's like crowd approval in Norway. And so there's going to be a lot of demos, and I've discovered this is always a risky talk because it's dependent on what's being broadcast, the signals that are out there. And as it turns out, we're in a giant concrete box. And so my signal reception isn't great. Normally the aircraft signals still get through, but then someone went and parked an aircraft carrier out in the harbor and enforced a no-fly zone. So I don't have a lot of aircraft data that I'm able to pick up. I do have a buddy in Nottingham in the UK that's also doing this and streaming this to a common Redis data in the cloud, Redis instance in the cloud. So we will have things to look at. We probably won't find much here. I was able to pick up a fair bit of boat traffic, though, so we can look at that at least. And this talk's going to be all over the place because it's covering a lot of topics. There's really two things that I kind of want you to get out of this. I'm hoping that you'll get out of this and say, software-defined radio is awesome, and I want to go buy one and do this stuff, because I think it's cool, and I think you should all think it's cool. And the other thing is that Redis is more than a cache. It has streams. If you come out of here and say, Redis has streams, I might use those someday. My boss will be happy, and I'll be happy. And so this talk's kind of all over the place. The radio topic is big and broad, and I'm just going to kind of plow through it. We're going to be talking about radio in a lot of different ways, the types of information that's being broadcast out there that you can listen to with a software-defined radio. We're going to be talking about aircraft and what kind of data they broadcast, and so that you can understand what you're looking at when you look at the aircraft. We're going to talk a little bit about streams in Redis, and we're going to talk a little bit about Redis. So we'll start with the obvious question. what the heck is software-defined radio? Well, in simple terms, it's a radio that you plug into your computer. So this is a software-defined radio. You can buy one on Amazon for, I think, about $30 US. It might be more here. But they're not super expensive. They're very accessible. And you plug them into your computer. You got a place for an antenna on the back. And all the data that antenna picks up gets shoved down your USB port to your computer. And the most important feature, especially when you're bringing these things through security at the airport, is that you label them properly. A software-defined radio is a regular radio, but with less stuff. So like these two radios I have here, there's a HF rig from Kenwood, and there's a cheap Baofeng handheld, like I have right here, a little HT. These radios, like this one I have right here in my hand, has a whole bunch of circuitry for receiving signals, amplifying signals, tuning to a particular frequency, and then decoding what it receives, whether it's demodulating the AM or FM or sideband transmissions or getting the data out of it or whatever. There's circuitry to do all this stuff. And in the case of this little radio here, this Baofeng, I think this is about the same price as a software-defined radio, but it's fairly limited and it doesn't have much range and it's kind of fragile, honestly. It's a little cheap. But they're a great way to get started. But it's got all this extra circuitry in it that's all about decoding and demodulating. A software-defined radio doesn't have any of that stuff. It has circuitry to tune and to say how much bandwidth you want to consume, and it's got circuitry to bring that signal in and amplify it, adjust the gain. But that's it. It just samples a swath of the spectrum and shoves it down a USB port. And then software can take that sample of just whatever's coming in from the spectrum and decode it, or demodulate it, or both. And so the software does the heavy lifting. And all the software is free, and so this means software-defined radios are cheap. They're much cheaper than a traditional radio. But they're also very powerful because you can do all sorts of things with that software. You can just listen to the radio, but that's like listening to the radio with extra steps. But you can also use it to get data and other things that are being broadcast. And so the easiest way to show explain what a software-defined radio is just to show you. So I'm going to go ahead and go into my first demo here. And so this blank screen is called a tool called SDR Angel, which is my favorite one to use. So let me go ahead and connect to my radio. Yeah, I know this font's tiny. I haven't been able to figure out how to change the font size on this, which is really annoying because I can't read any of it. Like amateur radio is traditionally, traditionally might not be the word, is a hobby that's often associated with old men, right? I mean, but, I'm sorry, but I don't know any old men that can read this interface. It is so small. What were they thinking? Anyhow, so in here I've got a little thing where I can just select my frequency, and this is a waterfall here where I can look at the frequency. I can see it visually. So let's embiggen that, and we'll go ahead and turn it on. And it's sampling the spectrum here. I need to get rid of that little voltage spike in the middle, crank the gain up to 11, and let's tune it to a frequency. So I have experimented a little bit and found that 105.8 is a radio station here. And hopefully this is working. Let's get the decimation down there. Okay, so you can see that's an FM, I mean, it's not obvious, but it's an FM broadcast radio station here. I assume it's here in Oslo. And if I add a demodulator, we should be able to listen to it. But you can see the signal already. Let's go ahead and hopefully this works. We haven't tested the audio, but I'll go for broadcast FM demodulator, hit apply. And is any sound coming out? Can you guys hear that at all? No? Well, it is demodulating it, I'm told. But there we go. I can't play this too long because we'll probably get a copyright strike on YouTube. But so it's playing music. This is just a radio, right? If I tune to a talk radio station, you get talk radio. And there's lots of frequencies out there broadcasting all kinds of stuff. I could tune to a frequency this radio transmits on, and then we would be able to see that as well. I can't transmit. If anyone here's a licensed ham, they are welcome to use my radio and send something, and I'll look at it, but we can do that later. But this is what a software-defined radio is. This signal comes in, the software is demodulating this signal, and we're able to hear it. So let's go ahead and stop that. And that was the demo. So this is kind of fun. It's kind of a neat way of interacting with radio. If you want to get started with software-defined radio yourself, there's some kits out there. These are the things that I bought. This is sort of my progression. I don't know if I recommend going down the progression that I went down, but you know, it's a cheap place to start. So the first kit I got was this RTL SDR kit. It's just this little radio dongle. I've got one plugged into my computer right now. I now have 3 of these. And it came with a small selection of antennas and connectors. And this kit was like about $50 US. And it's enough to get started. You can listen to anything from about 300 kilohertz up to, I think, 1.7 gigahertz. And so that's AM radio, FM radio, marine traffic, aircraft, everything in between. All the amateur radio, you can listen to it all, shortwave radio broadcasts. But the way it does a HF, which is the lower frequency stuff, the shortwave radio, is kind of a hardware hack. And it's noisy. And so I tried to get past this problem. I just had made my own antenna, and so first, to get past it, I went out and bought a nice loop antenna to listen to shortwave radio frequencies. And that worked better. I was able to pick up more signals, and they were stronger, but they were still noisy. There was a lot of noise just generated by the physical device. The SDR itself made noise when looking at shortwave radio frequencies specifically, from about anything below 30 megahertz. And so ultimately, I upgraded to this kit here, which has an up converter. So rather than try and use a hardware hack to get the SDR to listen to those really low frequencies, I think, by the way, the low frequencies are called HF, which stands for high frequency, which totally makes sense. But back when radio was new, that was considered high frequency. You had LF, MF, which stands for medium frequency, not something else. And then high frequency, which is HF. And then VHF, which you've probably heard of, is very high frequency. UHF, which you've also probably heard of, is ultra high frequency. These very imaginative names that we're using here. Well, anyhow, so the HF stuff doesn't work well with the SDR I have. But this up converter here, that device in particular, it's optimized for listening to HF. And it will take the signal in and just bump up its carrier frequency to a higher frequency where the software-defined radio can then process it cleanly. And once I got this set up going, I set up in my dining room in Columbus, Ohio, in the United States, that loop antenna just leaning against my dining room window. I picked up a radio station, a shortwave radio station broadcasting from Lhasa, Tibet, which is literally the other side of the world. This is why radio is cool, because these signals will you can literally listen to something. I mean, it's not a big deal that I could hear Radio Havana, Cuba, because they're pretty loud, and they're really trying to send propaganda from Cuba into the U.S., which is very entertaining. But picking up that signal from Lhasa was really compelling for me. And so this is the kits that I've gone through. If I was to do this over, I'd probably just buy a kit with an up converter to begin with and go from there. But you know, if you want to get into this, this is where you can start. There's a lot of other things to be bought as well. And it's a lot of fun. Software, all the software is free. Good news, right? There are 4 main software packages that I've looked at. There's this one called SDR Sharp. Any guess what platform and language that's written in? Yes, and unsurprisingly, it only runs on Windows. But it's actually a really full-featured tool with a lot of plugins. And so SDR Sharp's great. It's what I started with. If you want to do something on Linux, maybe on a Raspberry Pi even, GQRX is a good option. It's pretty basic, but it's an older piece of kit. It's perfectly serviceable and will run in tiny environments. So you can run this on older model Raspberry Pis and stuff. On my Mac for a while, I was using Cubic SDR. This works nicely on a MacBook. But really the one that I've landed on is SDR Angel. This is the one I was demoing earlier. SDR Angel supports software-defined radios that both transmit and receive. It runs on Mac, Linux, and Windows, and it's just got everything in it. It does all the things. I've used SDR Angel to just now to listen to audio, but you can also, it will decode various data formats right there in the program. Whereas like if you're using SDR Sharp, it tends to be, well, take the audio output that you got from SDR Sharp and then run it into another program using virtual audio cables, which is kind of a pain, whereas SDR Angel has it all built in. But its learning curve is steep. It's a little unintuitive how it works. So I'd recommend going for the learning curve, but SDR Sharp's not a bad place to start if you're a Windows user. So in addition to the audio there, I mentioned there's a lot of data formats being broadcast out there. There's a lot of people that use text-based formats and data formats. Morse code is still very popularly used by amateur radio operators, and so you can go listen to that. It's hard to machine decode because it's kind of like decoding handwriting. People key, and it's kind of they got a little bit of a randomness to how they do that. It's easier for us humans to match it, but it's hard for software. But it's still out there, and it's ostensibly a data format. There's people that are doing RTTY, radio teletype. This is an old standard of sending actual text data over the radio. It used to be used by newspapers to broadcast articles that their journalists had written to other stations in the world. And you can do this over shortwave. And so someone in like Tulsa, Oklahoma could send their report from Paris to Tulsa, and you could pick it up. And there's a lot of amateurs that still do this, and you can go spy on their conversations. It's good fun. They're usually saying, hi, what's my signal strength? It's this. What's my signal strength? Oh, it's this. Okay, thanks, bye. That tends to be the conversation, but sometimes they'll have more engaging things to say. Probably one of my favorite data formats that you can see being broadcast or transmitted over ham radio bands is APRS. This is the Automatic Packet Reporting System. It's a, who all here remembers or is familiar with X25? The networking protocol? A couple of you. Most of you are like, that's way down in the bottom of the OSI model. I don't care what to think about it. But so in ham radio, you have AX25, which stands for Amateur X25. And it sends radio packets. You can do TCP over radio, packet-based radio. It's slow. It's very slow. It's 1,200 baud, so it's really, really slow. Well, people would create TCP connections, little TCP networks over radio, but it kind of worked okay, but packet collisions was kind of a pain in the butt, and everyone could hear everything. APRS is sort of an extension of that idea that's simplified, where people just sort of shout out information about their location or whatever over these packets instead. And so it kind of works like this. So you've got various people out there that have associated APRS device broadcasting, say, their location from their vehicle. And so you'll see people on little maps, actually. You can look at the map and see where they're at and figure out who's speeding, actually. But they can, these packets, they all have their geolocation. They got latitude and longitude as part of their data. And so hams will do this to track their vehicles. There are various weather stations that people will mount on their houses. And these weather stations will give their latitude and longitude, and every 20 minutes broadcast the current weather conditions at that location. And this is an APRS packet that can be broadcast. And if you're in the area, you can pick it up and hear learn what the weather is nearby. And actually, even individuals with handheld radios or base stations can broadcast APRS packets and address them to other users, other ham radio operators, using their call sign. And you can do sort of like a text messaging back and forth over radio. All these are broadcast out, and they can be picked up by individual stations. So, like, I could just listen to them and decode them. They're often picked up by repeaters, and so someone will hear it, and then it will rebroadcast it, changing the header information, and send it out again so it goes to another station, and they can hop a couple times. And so by this way, if I can see a repeater, I can, from my handheld radio, I could send a signal to them, and then it can get out to like the entire state in the in this entire state of Ohio where I live. Even though like a little handheld radio like this has a range of maybe 5 miles. That'd be what, 10 kilometers roughly? And some of those repeaters are internet gateways, and this is where APRS is really neat because it's not only a radio thing, it's also an internet thing. So these internet gateways will receive these packets, send them into a whole cluster of servers on the internet, run by all the hobbyists that maintain this network. And then there are gateway programs where they can route it to software on the internet. So, for example, there is a weather bot. You can send a message from yourself to WXBot over radio. It will be picked up by a repeater and repeated a couple times. The gateway will send it in, and then it will go to a piece of software that will get the weather for whatever location you ask for. Then it will generate new packets. The gateway will send the packet back out. It'll go through the network again, and then you'll receive it back on your radio, like a minute later. And so there's this whole internet-based data can come out to radio, radio-based data can go into the internet. And it's actually a really cool system. There's all kinds of data floating around there, and you can just pick it up with any radio you want with a software-defined radio and decode it. Here in Europe, this is running at 144.8 megahertz, but it's a worldwide standard. It's everywhere. Everyone's using it. We might get lucky and be able to pick up a packet here. I'm going to try. But there's a website that aggregates all the packets to come in, because the packets all go into the internet. And so you can go to APRS.fi and view all the packets that are in a particular geography. So this is a screenshot from about a year ago in Columbus, Ohio, where I live. My house is, where is it? Right there-ish. Yeah. Oh, don't tell anyone. So, but yeah, APRS is pretty neat. There's other data packets out there. And we'll try and demo both of these. You want to just go to a demo and see if we can pick up an APRS packet? Or, well, actually, we'll hold off. I'm baiting you. Because I'm not sure I'll be able to pick one up, and then I'll have to go back and forth. I'll talk about a couple other formats, and then we'll see what we can pick up. And then we'll continue with the talk. I think that'll probably work better. Another common data format is boat traffic, AIS. All the boats, any boat of significance. I don't think your rowboat has this, but a yacht or an aircraft carrier would have an AIS transponder, which says, I'm at this location, I have this heading, this is my status, this is my identity, this is who I am. And this way you can know where all the boats are at so you don't run into them. And this information is broadcast at the latitude, longitude, heading, and speed. These are the frequencies it's broadcast at. And there's sites, if you've ever used like FlightAware to look for flights, which a lot of us probably have, there's sites similar to that for vessels called Vessel Finder and Marine Traffic. So you can go check those out too. So now, and then here's a screenshot from Vessel Finder showing the Great Lakes and the boat traffic there. So now let's go ahead and see if we can pick these up. There are some other data formats that are fun as well. If we don't pick up much, because this is a little bit of a radio dead zone, I have a fun trick that we can try, but we'll see what happens. Who here has a car that who here has their car keys on their person? Anyone? Excellent. You're going to be my guinea pigs. Okay, so let's kick this off again. I'm going to go to 144.8 megahertz. Incidentally, the encoding that's used in APRS is the same encoding used on a 1200 baud modem. So when you listen to them on audio, they have that same nostalgic screech. We'll see if one comes through here. I'm not super hopeful, but if we get one, I'll go to the packet demodulator. Which one says packet? There it is. But I haven't seen any come across yet. Oh, let me change the decimation here. There we go. So we see one come across. They look like little blocks of just signal coming down. But we'll see if I want to run for a little bit and see if we get one. You can see it. You see that there? It's a little faint. It wasn't powerful enough for me to decode it, but you can sometimes see them visually. Other fun things that you can pick up other than like APRS packets or boats is, there's a pager decoder. And so in the US, all the pagers are broadcast in the clear. Remember the old text pagers people would carry? Yeah, those are all broadcast in the clear and you can intercept them. And you know who carries pagers still in the United States? I don't know if it's true here, but doctors. And so you literally will see text pages coming across to say things like, yeah, patient so-and-so in room such and such needs their colostomy bag changed, right? Which is a total violation of privacy in the US, but it happens all the time. HIPAA violations per second. Another popular thing, or another interesting thing you can decode is you can get signals from space. You can actually get APRS packets from the ISS, which is really cool. But there's a bunch of old weather satellites, the old NOAA weather satellites that the U.S. launched, back in the 80s and 90s. They're still up there, and they're still sending their signals down. And so with the right antenna and a software-defined radio, you can get a real-time image from that satellite from space when it's overhead. Like, how cool is that, right? I got live images from space using a $25 radio dongle and a homemade antenna that I made from an old pair of rabbit ears from a television. And we're not getting anything here. This is sucking. So let's look for boat traffic. We'll see if we can pick up anything there. I was able to get a little bit when I tried it earlier. So I'm going to go to 162 megahertz. I'm going to add 2 demodulators. Yeah, you see those little blips on the side there, the lines that are coming across there? That's the transponder data from the ships. I'm going to go ahead and get a AIS demodulator here. I need 2 of them. And then this one is going to be at minus 25 kilohertz. This one's going to be at plus 25 kilohertz. And we should get a packet or 2 here. I can see them. You can see them when they come through. You see the little, the thing at the top bumps up, and then you'll see a little line of visual radio noise. Hopefully we can get something here. We're all staring at the screen hoping it's like one of his demos has got to do something. I literally picked up some earlier and now I'm not. Let's see if I move the antenna here. I mean, I should at least be able to pick up the aircraft carrier, right? Yeah, this is always the frustrating part. You can see the signals coming across, but they don't decode. So, well, let's go for one of the other fun demos. I'm going to use, let's go to 400. Actually, let's use a different piece of software for this. So who has their key fobs ready to go? Go ahead and get them out. I'm going to use a little tool called RTL 433. So a lot of commercial devices for short range operate around 433 megahertz, and you can pick them up with this little program here. So if someone has a car key fob, do you want to lock your doors real quick? Is it coming through? We should see it come across there. One of the things I picked up on this yesterday was I was testing it in the speaker room is tire pressure sensors. So the tire pressure sensors in your car that tell you have a flat tire, they use radio to broadcast that information. You can pick it up with this antenna and SDR. There we go. I don't know whose that was, but we got something. What's a microchip HCS 200? That sounds like someone's got an aftermarket key. Well, whoever's car it is, it's mine now. So, but the other thing I picked up on here, and you'll pick up in buildings like this, will be like thermometers or thermostats. They'll report the humidity and the temperature. The tire pressure sensors are always kind of interesting. It's like that Toyota has got you get one from each tire, and like I was looking at one yesterday, and the Toyota is like the software does it in Freedom units. Sorry, but it uses PSI, pounds per square inch. And a typical car tire is like about 30 PSI. And one of them was like below, like at 25, and the other one was all the way up at 55. I'm like, how are you driving this car? The air pressure is just way out of balance. So, okay, well, we got something. So that's something. Let's sally forth into the demo here. Or into the talk. So we got AIS. We didn't pick anything up. Boo. This is just a giant concrete box, and so this is always a risk with this talk. But the one thing that I can demo is ADSB, which is the transponder signals the aircraft broadcast. So every aircraft in the world, be it small or large, that's powered like from a Cessna to a helicopter to a jumbo jet to a military fighter has a transponder, and it will broadcast information about that aircraft at 1,090 megahertz. And that information includes, now the military ones can turn their transponder off, because obviously, or for obvious reasons, right? But all the commercial ones, they don't. They can't. But that data includes a unique ID identifying that aircraft. This one here happens to be Elon Musk's, because reasons. It's actually a 3-bit number, or a 3-byte number, and it's in hex. And so then there's actually data embedded inside of that. So like the first few bits represent like what country the aircraft is registered with and other things like that. They also broadcast their call sign. This is the radio call sign they use to communicate. For most commercial flights, that tends to be like the flight number from like Delta or Virgin or British Airlines or whatever. For private aircraft in the US, they tend to start with N. It varies quite a bit. Military aircraft, they put in things like Iceman and Maverick. And this one is Elon Musk's tail number and call sign. You also get the altitude of that aircraft in feet. That's the international standard. The speed in knots, the heading in degrees, of course, and their location in latitude and longitude. And so they're broadcasting this all the time, and you can use an antenna to pick it up. And I've actually got a purpose-made magic wand. It's an antenna specifically made to hook up and monitor ADSB signals from aircraft. And so I'm hoping we can find something. I think this is going to be a bust. But for my software demo, I do have a friend sending data in as well. So we're going to go ahead and try it. The tool that I'm going to use is called Dump 1090. Dump 1090, through happy coincidence, was actually written by the same guy who created Redis. He was, I guess, having to deal with his family over a holiday weekend around Christmas, and decided he would write C code instead, because that's how he chose to live his life. And he wrote Dump 1090 to read all this transponder data. And so I'm going to try and run this and see if we can pick up any aircraft. I'm not super hopeful because of the no-fly zone and the concrete and rebar box that we're in, but we'll see what we get. So if I go here, I go dump 1090 --net --interactive. And I need to swap out my antenna here too. So get the end of that antenna there. Disconnect the other one. So, oh no. I unplugged my SDR. Hopefully that's not a problem. Shouldn't be. There we go. Screw it in there. Plug it in. Get my antenna out. And I'm going to go ahead and run dump 1090. And then it gives us a display. And so I'm going to stand here like a wizard with my magic wand and hope for the best. Hey, we picked something up. Excellent. Couple of things. There's Doc 63. No idea what that is. Is Doc an airline maybe? Maybe it was Doc Flight 63. It's an altitude of around 1,200 feet, so it's pretty low. That could be... It's a helicopter. Yeah, I was going to say it's probably a helicopter. We got IBE 34 DC at 13,000 feet, and looks like they're climbing. NAS 1104. Excellent, excellent. So we... Doc stands for doctor. Okay. It's a doctor helicopter. So it's a doctor helicopter, okay. So the demo gods have smiled upon me and actually give me something to look at. Thank you, demo gods. Let's go ahead and I want to show you something the software does. So if I go use Netcat to connect to it, it broadcasts these out on a TCP port so you can listen to them. So if I go to Netcat localhost, I'm typing with one hand, it's always awkward. Go to 30,002. So this is the hex data that those transponders are broadcasting. And so you could easily connect a socket to this, parse that data. But it's easier. If I go to port 30,003, think you could parse that? It's just CSV data. And actually, it gets even easier because I use JavaScript to build my little demo to consume this data. So I've written something that will talk to dump 1090, pull that data out. It just connects to dump 1090. But there's a library that knows how to talk to dump 1090 already and knows the format that this spits out, and I just have events in JavaScript, and so I just get an event whenever a message arrives. And so it's super easy. So let's go ahead and kill that. We'll leave dump 1090 running, and then I'll show you a little bit of what I built, and then I'll demo it. So we've got what, about 25 minutes left. I think we're good on time. So what I've done is I've used dump 1090 and the software-defined radio to take all those broadcast messages and I feed them into Redis in an event stream. So message comes in, append to the event, just keep appending to the stream. And then I consume that stream to put all the aircraft in our area on a map. So I've built FlightAware. The version of Redis I'm using to do this is Redis Stack. Redis Stack is regular old Redis with some extra data types and commands that'll let you manipulate JSON documents. That allows you to do search against those JSON documents and hashes, which I've implemented search in this particular demo. Also adds probabilistic data structures, which I talked about yesterday, and time series data as well. And so I've built probably an over-engineered piece of software just because it was fun. I'm going to call this a microservice architecture, and people who actually know about microservices can tell me I'm wrong, and that'll be fine. But what I've done is I take those signals, and I've got a series of radio ingester services running. And so these radio ingesters, their purpose in life is to just talk to dump 1090 and shove something on a stream in Redis. And so that's what they do. They shove data into a stream. I will be running it here locally, and my coworker is wanting to run in Nottingham in the UK, and we have a cloud instance of Redis that we're shoving this data into. I've got a radio consumer service which consumes that stream and then updates hashes in Redis with the most recent status of that aircraft under a key of like airplane : and then the ICAO number. And then I have a flight API which will allow you to search and query all of those hashes. And so give me all the aircraft that I could detect that are above 20,000 feet or that are heading north. And then I have a flight event service which just publishes a WebSocket of the messages coming off the stream. Those both feed into a little UI with a little gateway in front of it, and then we've got a little flight tracking app. We'll talk a little bit about how the radio ingester works first. I mentioned that there's a library for Node that knows how to talk to dump 1090. It's called SBS1, so I just use that. And I call create client, give it a host name and a port, and then I get a Redis client as well using Node Redis here. And then when I get a message, all I do is take the SBS1 client on message, and then I get a JavaScript object that has the data that I care about. So this was stupid easy to build. I actually built it live on stream over a period of 3 weeks, like 2 hours every Friday. And then you process that message. It's got some weirdness to it, and the processing of the message isn't really all that interesting to code. The date's in a weird format. Sometimes there's fields missing, and so it's just a bunch of code to handle those sorts of things. Make sure we're sending everything as strings and sending them into the event stream. And so let's talk a little bit about event streams in Redis and event streams in general. I never want to assume that anyone knows anything. That seems like a good way to live your life. But a lot of developers have used event streaming. Some of you haven't. So this is just a super quick introduction to the idea and how they work in Redis. So an event stream is, well, it's an event. It's a stream of events, right? It's a chronology of things that have happened. And so you'll have a thing that happens, and there's going to be some data associated with it. And then you have a timestamp, an ID for that event. So this could be, in our case, an aircraft transponder broadcast its altitude. And so it gets assigned an ID. And then these stack up on top of each other. In Redis, specifically, the IDs are actually a timestamp. And so the first part of the ID is the Unix epoch time in milliseconds. And the sequence number is in case you get more than 1 millisecond. And but this is event stream just represents that sort of a thing that has happened, a point in time with data associated with it. I kind of think of them sometimes like log files. This happened, then this happened, then this happened, but a little more structured. And so then as events come in, they just stack up chronologically. It's append only. You can't go in and like insert something in between. It's always just stacking up, like a log file. And that's sort of streaming in 60 seconds. It's a useful data structure for what I'm trying to do because I have literal events that occur and they have a chronology and I don't need to go in and delete things in the middle or insert things out of order. It's just I receive messages and they come in. To use a stream in Redis, you use the xadd command and you provide a key name for that stream. Each stream lives in a key. You give it an ID. In this case, I use star and it'll generate an ID like I just described. And then you give it key value pairs. So here we're adding Elon Musk's aircraft ID and call sign. And then Redis, to read these streams, you call xread. And you give it a stream or streams, and you give it a ID that you want to start with. And so this will read everything from that ID to the present. So I've given it ID 0-0, which means beginning of time, which means you get everything. Now I've only added one thing, so I get the one thing back. We'll add something else. And then here we can see that since I've added something now, I get an ID back. What was the point of this example here? The main point here is to show that if I pass in an ID, it gets everything from that point forward. And so generally, you read something, you get an ID back, and then you read the next group of things, and you get an ID back. And you can limit these with a count statement. So here I'm saying xread count 10. So give me, we might be reading from the beginning of time, but I want the first 10 things, and then I'll process them, and then I'll ask for the next 10 and the next 10. And I can just keep daisy chaining those IDs along. So this is the commands that you use in Redis. In code, it's actually pretty much the same. This is Node Redis. In JavaScript, we call xadd, and you give it a stream key and a star, and the event is just a JavaScript object. It's equivalent to calling this. So I've got some code here on the flight events. It's uninspired WebSocket code, so I'm not going to go into it. You can go look at the slides yourself later if you'd like. But the main thing from a Redis point of view that is worth noting is that when you call xread, you can block. And so in this command here is reading the stream, and it's blocking and waiting for 5,000 milliseconds. And then we're reading from the special ID of $, which means give me anything new when it shows up. Don't give me anything that's on the stream right now when I call this command. But if someone adds something, tell me. And so if you want to start consuming the end of a stream, this is how you do it. And so then we add something, and then it responds back. And then once you do this, then you can pass in the ID of the previous thing and do a block again, and then you're reading the end of the stream. And so this is JavaScript code that does the same thing. We'll just skip through this. And then the event we get back needs some conversion, so we're saying, well, if this value isn't here, then don't set it, that kind of stuff. So nothing special here. And then here is the WebSocket code to send WebSocket streams down here. And honestly, this code's kind of boring. I'm just going to skip it. It's out there on GitHub. You can play with this yourself. What I'm going to do is I'm going to demo the tracking aircraft application. So let's do that. That's the exciting part. That's what everyone came here for, right? So let me go ahead and kick off. Now I don't have an aircraft. Docker compose up. So that's running. Oh no. Well, we'll let that go for a bit. Oh, come on. Come on, demo gods. Be good to me. I promise to sacrifice a Raspberry Pi in your name. Well, while this is loading, come on. We got aircraft earlier. It was so great. Well, let's go ahead and take a look at what's in Redis right now. So while this is happening, so my friend in Nottingham is running the same thing. He's feeding this into Redis. I'm not getting any aircraft, but he is. And this is the event stream called Radio Events. And if I refresh this, you can see that he's got Radio Nottingham, and the time is 11:39 and 24 seconds, which is now. Is it now? Yeah, it is, because he's in the UK, which is an hour in the past. So we're getting Should be getting new data coming in here. Maybe not. Okay, so I've connected. If I get any messages, they're going to go in there. I'm going to go ahead and run the other half of this thing. So this is just the radio ingester. We'll go ahead and run the other one, which again is going to need a download, so we'll let that do its thing. Yeah, I think Simon's thing crashed. This is going to be the worst demo ever. Well, we'll let all this stuff build. Oh, there we go. That actually wasn't too bad. That was pretty quick. And so we can go in and take a look. Let's launch a web browser. Brave. And we'll go to localhost 8080. And yes, you may use my position. So there's a map. It knows where we're at. Let's see if any aircraft show up. Come on, Simon. See it. Well, this sucks. You know that awkward feeling you get when you're trying to do a demo and it doesn't work? Awkward.
There's a Norwegian plane headed for us.
Is there? It's heading right for us? Yeah. It's heading right for us. Rabbit, 5 o'clock.
A couple of minutes.
Yeah, hopefully. Oh, maybe if I just stand up really high. Right? Every time I talk about this demo, someone's like, well, why don't you, use your radio to generate data so that you can pick it up on your antenna? And it's like, well, because that would be as illegal as hell. Turns out the aviation authorities don't like it when you generate false aircraft because everyone tries to fly around them. It's a big deal. That's a good way to go to prison. And it looks like my ingester died. I'll kick it off again there. So I might be able to do something else here. I have let's try this. So I created a way to inject fake aircraft into, it's the flight injector. And so I recorded several aircraft flying into my home around Columbus, Ohio. So I can inject some aircraft into dump 1090 because dump 1090, in addition to spitting out the hex data, you can shove hex data into it and it will display it. And so, and I haven't tried this in a while. Let's see, cat server.js. It's looking for, I think the file's hard-coded. Is that the file name I have? It is. Yeah, so node start. Node serve. No, it's npm serve. npm start, that's it. There we go. So now it's reading the data. It's injecting data in. So you see data showing up. It's not coming from the antenna. It's being manually injected, although if we pick up something locally, we'll see it. And if we go to my app here and zoom way, way out, go way, way over to Los Estados Unidos, down here, we should start seeing aircraft popping up here. But we're not. What's going on here? Oh, because that crashed. There we go. I recorded like a half an hour of data, so it's certainly coming in. And then refresh this. Zoom way out again. Go across the Atlantic. There we go. So this is aircraft that I recorded previously in my home. I live right up here. Ohio is about 300 kilometers across. And so I picked up stuff all the way over here in Indiana and pretty much in the entire state. So it's pretty cool. This is what it would look like. If you click on these, that will show you the aircraft information that it's picked up. So this is, that's probably a private plane. That is, we don't know the number of that one yet. There's Southwest Airlines Flight 738. If I click on that, it'll take me to FlightAware, but this flight was like a month ago. So I don't know what it'll do, what I'll actually get when I click on it. Okay, expected to depart in 3 hours. So it's not obviously where it's actually at. But you can also click on this number here, and this will give you the API where you can search these different aircraft. So I can find aircraft heading north. Okay, south. There we go. So, oh, actually, it says radio NDC Oslo, but it's lying. So we're picking up some aircraft that are heading north. So we were able to search this aircraft and stuff. It's not the real-time data that I was hoping to show you all, but at least we got something here. They'll fade off after a while. You'll see them move. Actually, fun implementation detail. I had a hard time getting the aircraft to rotate. I tried doing like a little CSS trick to rotate the image. Totally wouldn't work. I ended up creating 16 airplane icons, and I just look at the heading and I just changed the character out. And so when you watch these up close, you can see them move, assuming it's still running. So yeah, that one moved just as I flicked away from it. So, but you will see them move in real time. Let's refresh and see if we actually are picking up anything in Oslo yet. Of course not. So, well, anyhow, that's my little demo. We got about 8 minutes left here, so let me wrap up. Apologies, that could have been way better. But, we got a couple minutes. Let's do questions just after this, all the CTAs that my boss wants me to do. So if you want to check out this stuff on your own, you can get Redis Stack at this location. And all this is out on GitHub. This is the SDR software that we looked at, that I mentioned earlier. Here's the AIS trackers if you want to track boats. Here are some online ADSB trackers. And Dump 1090 is out there on GitHub. It's just written in C. You can download it, compile it, do what you like. We have a Discord server at Redis. Go check that out. Discord.gg/Redis. Free classes on Redis University, including one on streaming. And you can get a free cloud instance. This is the cloud instance I'm using for this at redis.com/try-free. Here's the link to take you to the slides, codes, and whatnot. So if you want to play with this stuff yourself and do a better demo at home than I did here for you live today, you can go do that. And now I'll take some questions if there are any. Any takers? I'm looking for hands. Oh, yeah.
If you want to listen in on the NOAA satellites, what kind of antenna would you have?
So the question is, if you want to listen in on the NOAA satellites and get those live images from space, which is cool. I haven't done this myself yet. I've tried it with the wrong antenna. And I got something that vaguely looked like a cloud and mostly static. But there are several antenna varieties, but the easiest one by far is you can take an old pair of rabbit ears, and the instructions are online, and you just aim them out vertically like this at a specific length and at a specific angle, and then just face it, I think, west, I can't remember, in a specific direction that works with the satellite. And that's a very cheap antenna that you can literally just take a pair of old rabbit ears and a soldering iron and make it work. And so that's the most accessible one. You can make like complex like ones where you have got like a helix around a cord, and then you're holding it like this and you're trying to follow the satellite as it goes overhead. And that will give you a better signal, but it's also, they're harder to make and they're harder to operate, and you have to be there just at the right time. I could take those rabbit ears and mount them on my roof and then just have like software that knows when the satellite's going to be overhead and just grab the image periodically. It's something I'd like to build, actually, is a little Raspberry Pi space image capture thingy. So, great question. Thanks for asking. We got any other questions? If not, I'll let you go get some lunch. So, well, cool. Well, thank you very much. Apologies for the demo being sucky, but the tech is still really, really cool. So, thanks.